Okay, hello everyone. So in this video I wanted to discuss about square root decomposition. So the agenda for this is to go through what square root decomposition is and how did it originate. So how did we come to the conclusion for using square root decomposition. We'll also discuss the proof for that, and we will take a simple example problem for studying how this technique is used to solve uh, query related problems. And we'll also discuss an implementation, which is a generalization technique for solving similar problems. So let's dive into it. Okay, so first of all, what is square root decomposition? um, it tries to basically split the data into smaller chunks and stores the answer for those smaller chunks, so that whenever you're fetching answer for a larger range, uh, those answers can be pre-computed instead of traversing again and computing them again. So the main purpose of decomposition is to store accumulated results on disjoint parts of the array. Usually you will see this technique used on arrays only. So you will be given certain ranges, and you need to find out some result, for example sum, x, or maximum, minimum, anything. So we divide the array into smaller parts and store the results for those smaller parts, and whenever some query comes which asks for certain function in that range, so we traverse through these parts and get the required results. So let's start with an example problem. So this is a simple problem. As you can see, we need to handle two types of queries on the array of size n. First type is a point update. We need to update the index id with the value, and for the second type we need to print the sum from the index L to R, subarray index from L to R. So this is a standard problem. This can be solved using segmentaries, but for this video I just wanted to get a kickstart of how square root decomposition can be used in this, so that it can be helpful for other problems as well. Okay, so as we went through the definition, we are going to uh, divide that into smaller parts and store the results. So let's go ahead and see how we can do that. Okay, so let's say we were given this array and we have decided to split this array into blocks of size k. So as you can see, this whole part from index 0 to n minus 1 was the entire array, and we are now splitting it into some blocks, and each block lies on some range L to R. So first block, or we can say 0th index block, stores the result that we are trying to achieve in this case, which is sum from 0 to k minus 1th index, and second block from k to k minus 1, the next basically next k elements, and so on. So block 0 stores the sum from 0 to k minus 1 array elements, block 1 from k to k minus 1, and so on. So this is basically the translation of the definition for square root decomposition for our problem, and let's see how this is going to transform. So let me also discuss what will be the naive way of computing this. So updating the index with value is a constant operation which can be of one operation, and the second operation can have the time complexity of order n, because we will traverse through all the array elements and we will find out the sum. But now let's try to find out how this decomposition will change the time complexity. So assume this k is not fixed yet, so we are assuming it as a variable, and which will basically we'll find out a better for what value of k the time complexity is minimized. So that is our main aim. So let's go over the time complexity computation for this technique. So basically now we have divided that into k disjoint blocks, and each block will store their accumulated results. In this case we are computing the sum, so the first block will store the sum for that range, second from that range, and so on. Now how will the first query change? So first query is still updating the index with value, right? And a particular index will lie in some block, only one block. So let's say we are asked to update the index 2k minus 1 with some value. In that case what we can do is we'll simply go in, we will find out what block this index lies in, which can be found out by computing the value of index divided by the number of blocks or the block size. So 0, any value which is the first range divided by k will always return 0. In this range it will return 1, in this range it will return 2. So basically we can find out in which block the given index id lies in, and we can simply remove the old contribution of this value, old value which was present from this sum, update this index with the value which you want to update with, and again add that contribution in that respective block. And that operation will obviously take order one time, because we can find out which block it lies in constant time and update the sums in constant time as well. So first query is still order 1, no issues, same as the naive way. Now let's figure out what type 2 query will take. So as we have divided that into n parts, right? Blocks of size k, then the number of blocks will be n by k, or the ceiling of n by k. Now this case can be a little tricky, so let's go over this diagram that I've made. So let's say the second query comes and asks for some sum for L from L to R. Now in the worst case what can happen is not necessarily all the blocks are going to coincide and perfectly overlap with our query ranges. So in this case what can happen is, let's assume this orange are the block indices that our square decomposition is storing, and query left comes at this and query right comes at this. As you can see, this block block index 1, this block basically completely lies in the query. This block completely lies in the query range that is given to us, which is denoted by this blue color, and we can fetch the sum from it in constant time, no issues. But the issue can be these green portions cannot be treated as a single entity, right? So this green portion, they are not a part of a complete block, and we can't simply fetch the sum from this block, because this block is only storing the sum from 2k to 3k minus 1, and we can't ask it to give me the sum from these three indices. So in that case what we will need to do is we traverse this index naively. So if we had to traverse these indices naively, green indices, then that operation can take order k time, because basically this edge case can happen only for two blocks, the leftmost and the rightmost, because the middle blocks will be completely covered and the left and the right part may or may not be covered. And if they are not covered, we'll simply traverse to them and get the required results. And we are only traversing order k elements in this case, because each block will contains exactly k, but depending on the query range and the constraints, we will go through O of k elements. So this is how we arrive at order k time complexity for partially covered blocks, which is at most 2 in this case. So as we saw, only the leftmost block in that query range that is given to us, and the rightmost can be partially non-overlapping. So basically I have divided the query 2 into two parts, going through all the completely covered blocks and going through partially covered blocks to get the required sum. If you are going through all the completely covered blocks, there can be at most n by k, right? Because we are dividing array into blocks of size k, there can be n by k blocks, and in worst case we need to go through all the blocks, and each block will give sum in constant time. So in all, order n by k time. Or partially covered blocks, there can be at most 2 for a given query, and we can acquire the sum in order k time as we saw earlier. Hence the total time complexity for the type 2 query after dividing the array into blocks of size k will be order n by k plus k, the sum of these two. So this is what we arrive at currently. This initially for the naive computation was order n simply, but in this case we have arrived at order n by k plus k. So we still haven't figured out what value of k will give the minimum time complexity for query 2. So let's derive that. Let's find out the most optimal value of k. So let's go through the proof. So we are interested in finding out for what value of k the time complexity n by k plus k will be minimum. So let's define a function. K is variable in this case and n is a constant for a given array. So we have defined a function f of k equals to k plus n by k, which is the time complexity required for query 2. Query 1 is still order 1, so we are not considering it because there is no need to optimize it further. Now let's see, whenever we want to find the minimum value of a function, we differentiate it with respect to the variable. So what I've done here is calculated f dash of k, differentiation of the function with respect to k, and for the minima, basically the graph for that minima will be the slope for that graph will be 0 at the point where it is minimum. Hence we are saying that the value of that function, the differentiation, the slope will be 0, equating with this standard process for finding the minima. By this way we derived at k equals to square root of n. So we derived that k equals to square root of n will give us the minimum value for this function, and this function is no other than our time complexity for query 2. So this is how we arrive at the square root decomposition. So we understood that dividing the array into blocks of size square root of n will give the least time complexity, and now let's see what that time complexity will be. If we substitute k equals to square root of n, we'll get square root of n plus n over square root of n, and overall it turns out to be order square root of n for each query. So given one query, it will give us this sum in that range in order square root of n time. So the overall time complexity for the solution will be q times square root of n, which is obviously less than q times n, which was the root force solution that we were initially thinking. So this was the proof, or I might say intuition, for arriving at square root decomposition. So let's try and go over the implementation now. So I've taken this from the USACO website, and let's see. So this is like a specific use case implementation for the problem that we discussed. So we are defining a square root decomposition structure, assuming we are using zero-based indexing for the buckets or blocks. Now what they basically do is we are assuming the block size, so this is square root of n in our case. Nums will be the actual array, input array a, which is given to us. Blocks will be storing the sum of a particular block. So blocks of I will store the sum of elements from range 0 to k minus 1 and so on. So the constructor initialization part is same. As we saw, the block id can be computed by finding the index divided by the block size, as we saw in the diagram here. So index divided by the block size will give the block id that we want to store the sum inside it. Next, for the given array, we'll compute basically all the sums will be computed for all the blocks initially. Next, let's see how we handle the queries or updates. Sorry, updates will be of 1 in our case. So x by block size will be the block in which xth number or xth index lies in. So we are going to subtract the old value from it. The blocks contains the sum of nums of x, which was the old value, but we want to update it into the new value. So before updating into new value, we are basically removing its contribution from the sum. We are updating it with the new value, then again adding that contribution to the sum, so that it is consistent with the changes that are happening in the array. Next, in this case, they have basically used prefix some kind of technique. So sum of elements from L to R will be sum of the first R elements minus the sum of the first L minus elements. So that way you don't need to handle two edge cases differently. So the leftmost part will not be like the rightmost. There can be at most one partially filled block if we handle the queries this way. So basically, if we find out all the completely overlapping blocks sum in this loop, and in this loop we are basically iterating over the remaining elements. So if I had to visualize this, so if we are asking it from query left to query right, we are asking our square root decomposition to give me the sum from 0 to query right, and in that case query left will come here, and there can be at most one partially lying block, so that way we don't need to handle both cases separately. So that is basically the intuition. You can implement it any way that is preferable to you. And again, this is finding the sum from first R minus first L minus 1 elements. And again, this constructor will initialize the bucket size, or k in our case, to the square root of n value. And this is again standard technique. So this was we are storing the values in 0 index, that's why we are converting it into 0 index. So that was all for the implementation part. Let's go over some of the applications. So we can use this technique to, like, Mohs algorithm uses this technique to find out answers to some offline queries. Some of the applications include finding distinct elements in range. So you are given static queries, there are no updates, but you need to find the number of distinct elements in each of the ranges. So Mohs algorithm can help you. What basically it does is arranges the queries such a way that moving from one query to the other, there can be at most square root of n new added elements in that range that we are considering. So that is the basic idea. We can discuss it for any other video. You can also use range updates and range queries similar to lazy segment trees by performing some updates in the implementation that we saw earlier. Then sometimes in competitive programming you can find there are weak test cases, so you can use this technique to exploit a weaker constraint, I can say. So you can use this for multiple problems, and usually whenever the constraints are up to the 10 to power 10 to 5 or 5 times 10 to 4, you can use this, because q times square root of n can basically time out, or there can be some strict bounds on the time limit or expected solutions. So make sure you use this technique whenever you find this type of constraint, or it may be a hint to use such technique. Okay, so next I wanted to go through how you can generalize this technique to, instead of every time finding out what needs to be stored where and how you are going to compute this, it's better to define a template type structure so that you only make changes wherever the problem variations differ. So I have taken this as a reference from Ashish Gupta's GitHub repository. So this is a solution to this problem, I guess. So I'll just explain how you can make your own structure, which is relevant to solving this type of problems. So what we do is basically, this is a function which will return us the answer for any query in L2R. This query will update the range from L2R with some value x. The function can be anything. You can modify this code according to your needs. I will also link this in description. How we initialize these square decomposition blocks, and each block has its own function. So the block can be initialized with some predefined values. There are semi updates, so partial queries or partial updates. So the problem we saw only had a point update, so there can be range updates also. So you can change this template accordingly, and you can uh, alter this code according to your problem definitions. So there can be three update functions: full updates, full for the blocks that completely lie in the query ranges, and for the blocks that partially lie in this update, and a wrapper function update, so that you call an appropriate update function depending on the range values that are given in the query. Next, for query, you can have partial queries which are iterating over the actual indices which partially lie in the query ranges, and some full queries, as we saw. If you are storing the sum, then this operation can be constant time, and a wrapper function for calling the respective query functions, full query or semi query, depending on whether the query ranges lie completely inside the block size. So this is how you can change this. I will link this in description. You can change it according to your needs. So that's it. That's what I wanted to discuss in this video. So if you like this video, you can share it among your friends and subscribe for more such content. Okay, thank you.